In this unit, we're going to look at a different type of coordinate system. Now, throughout our math years in algebra, we focused mostly on the Cartesian coordinate system, where you have an x and a y, and the x values are horizontal, the y values are vertical, and everything is very rectangular. Well, there are lots of other systems out there, and the one we're going to look at is called the polar coordinate system. So instead of x and y, we're going to deal with r and theta. So if we look at this, instead of a rectangular grid, we have circles. We still have an origin, so that's still the center. Origin. And instead of an x-axis, we have what's called the polar axis. So that's kind of our starting point. Now the grid, instead of being rectangular, it consists of concentric circles radiating from the center. So every circle is a different radius value, and then the lines that come out from the center, that's a different angle measure. So we can still find a point on the grid using a radius and an angle measure. So we're going to further define this system and learn how to use it. Okay, again, we can locate a point. This is the type of coordinate that you're going to see. We can locate it by stating the radius and the angle. So again, r is the radius, that's the distance from the center, and then theta is the angle made from the polar axis. So we can have positive or negative radii. If the radius is positive, that means the point is going to be on the terminal side of the angle. So a positive radius behaves as we would expect it to be. From a central angle, it's going to be on the terminal end. So let's take a look at this. We're going to graph a point and have a radius of 3, and we're going to have an angle of 2 pi over 3. We deal in radians in this unit quite a bit. So let's mark off our graph. Every two, well, here's our polar axis. It's always good to put the polar axis in, and every 2 lines it's going to be 30 degrees, so pi over 6. This is pi over 6. Erase that guy. This is pi over 3. That's going to be pi over 2. And 2 pi over 3 is going to be this guy. So I'm just graphing a point, and that point is going to lie on the line that creates the angle of 2 pi over 3 from the polar axis going counterclockwise because it's a positive angle. And then I'm going to count out 3 circles from the center. And that point P is going to be right there, if I can label that right. There's point P. So a second example, we'll graph 5 comma pi. Again, if this is our polar axis, pi is 180 degrees, so he's going to be 180 degrees from this side over here, and we're going to count out 5 rings. 1, 2, 3, 4, 5. So there's where my point's going to be. That's point Q. So positive radii, positive angles represent a pretty straightforward process. Now when the radius is negative, it's a little goofy. The point's going to be 180 degrees from where you would expect it to be, because a negative radius is a reflection through the origin. So the point will be on the ray opposite the terminal side. So let's take a look at that. Here we have negative 3 comma 2 pi over 3. So we found that angle before. The angle of 2 pi over 3 is right here. But instead of the radius being on this terminal side, he's going to be 180 degrees away from that. So it's kind of hard for me to visualize here. If I dot in this angle, he's going to be down here, so 3 units away. So he's reflected through that origin. There's point P. A second example, if Q is negative 1 pi, then here's the polar axis. Normally, a value of 1 pi would be here, so he's reflected through. He's going to be right there, sitting on the polar axis. So it can be a tiny bit confusing when you're dealing with negative radii. And just one more thing, the way we denote the angle is the same as we've always done. If theta is positive, then the angle is going to sweep counterclockwise, and if it's negative, it's going to be clockwise. We'll talk about negative angles next. Alright, so a positive angle and negative angle tells you which way you're sweeping relative to the polar axis. So we're going to graph a point S is 3.5, and theta this time is going to be negative pi over 2. So here's my polar axis. Now, instead of going this way to positive pi over 2, I'm going to sweep this way, and this is negative pi over 2 down here. So I'll mark that, negative pi over 2, and I want to count from the center 3.5 rings. 1, 2, 3, and the halfway point's right there. So 1, 2, 3, he's about right there. There's S. We're going to make T be negative 2, so a negative radius and a negative angle. Gets a little wacky. A negative angle means I'm going to be going counter or clockwise, and 30 degrees is going to be here. So this point, this angle represents negative pi over 6, but I also have a negative radius. So normally, if I were to graph positive 2, negative pi over 6, I would be here. However, I now have to go through here and reflect him on the other side. So just to try to take a look at where that's at, he's going to end up here. Negative 2, 180 degrees from the original point. So let me see if I can, it's kind of hard for me to see on this iPad here. He's going to end up there. There's T, because that is a straight line 180 degrees from the original point. Alright, in the Cartesian plane, we can really only locate one point with one set of numbers. It really can't be represented several different ways, but the polar coordinate system, because of positive and negative angles and positive and negative radii, and ending up in the same spot, we can represent the same coordinates several different ways. So you think about this, and we will cover this in class. If I have the point 3, 5 pi over 6, how else could I locate that same point using either positive or negative radii or coterminal angles? And we'll talk about that one in class. Alright, so we're skipping to kind of a third, or the kind of the center of the next page, because we're going to do the renaming in class. We're going to convert now between polar and rectangular coordinates. So rectangular coordinates, I can always create a right triangle in the Cartesian plane. If I have a point xy, and he's sitting out here in the Cartesian plane, I can always create a right triangle. So this would be x, this would be y, but I can also redo that using the radius and the angle. So we'll talk about first if we're given x and y. So if we're given the rectangular coordinates x and y, well, the radius can be found using Pythagorean theorem, and when you get done, it's the square root of x squared plus y squared. And the angle can be found using the inverse tangent of y over x. We've talked about that before. So that's how you can go from rectangular to polar. Now, going from polar to rectangular is a little bit easier, and we've done this before. If we're given the radius and the angle, then x is going to be r times the cosine of theta, and y is going to be r times the sine of theta. Now let's think about why that is. The cosine of theta is x over r. The sine of theta is y over r. If you cross multiply, this is what you end up with. So these are handy formulas to remember, and they will allow us to convert between the two different coordinate systems. Alright, so we're going to convert 4, 2 pi over 3 to rectangular coordinates. So my radius is 4, and my angle is 2 pi over 3. To convert that way, I know that my x value is going to be 4, times the cosine of 2 pi over 3. And my y value is going to be 4 times the sine of 2 pi over 3. We're going to keep these things exact. We're going to use special triangles when we have special angles and keep everything exact. I don't want to see a whole bunch of decimals on your paper. 2 pi over 3. This goes back to our trig unit. 2 pi over 3. That's going to be in the second quadrant. And the reference angle is pi over 3, which is 60 degrees. Cosine of 60 is 1/2. Cosine's negative in the second quadrant. So my x value is 4 times negative 1/2. He's going to be negative 2. And then my y value, y is positive in the second quadrant. That's going to be 4 times positive radical 3 over 2. So that's going to be 2 radical 3. So my coordinate is negative 2, 2 radical 3. That converts a polar coordinate to a rectangular. So we'll finish by converting a rectangular coordinate to polar coordinates. There are two ways to do this. I'm going to use the formulas, but if you recognize the ratios and special triangles, you can do this a bit more intuitively. But I'm just going to do this using our formulas. We know the radius is going to be the square root of x squared plus y squared. So the radius here is going to be the square root of 2 squared plus, remember, one of the biggest mistakes I see is you square a negative number and you tell me that it's negative. Please don't do that. That's not good. So r is going to be radical 8. Simplifying, my radius is 2 radical 2. Theta is going to be the inverse tangent of negative 2 over 2. Now, we're going to talk about this more in class. You have to be careful when you use your calculator to find the angle, because you got to look at this and see which quadrant it's in. Negative 2 is in the fourth quadrant. So over here, if you put that in your calculator, you're going to get a value of negative 45 degrees. That's okay, because it's a fourth quadrant angle. In radians, it's negative pi over 4. So my polar coordinates end up being 2 radical 2 and negative pi over 4. So in class we're going to talk about what happens when you have a second quadrant or a third quadrant angle, because your calculator doesn't help you with that. And then we will also work some more examples so we really get this process down and remember our special triangles again.